Hello everyone, and then welcome to another video. Okay, so in this video we'll be treating three-phase circuits. Okay, so we've done a couple of subtopics under what apply electricity and what electrical engineering. So we are to treat three-phase, after that magnetic circuits, and then we are done. Okay, right. So without further much ado, let's dive right into this video. Okay, in case you are new to this channel, kindly subscribe, hit on the bell icon so that you don't miss out on any uploaded video. Like the video, share, and let me know your questions in the comment section. Okay, right. So for three-phase circuits, we have what we have the star arrangement, okay, which is in this form. Okay, so we have A, B, C with lines. Okay, so three-phase circuits are joined with lines, so there are three voltages joined with lines. Okay, so you normally see them on what the rows. Okay, so they are the main sources of what voltages. Okay, that's where they split up and then they are being connected to what other lines to what join to our homes. Okay, right. So we have what star and then we have our delta. Okay, right. So one thing you need to know is that what these three-phase circuits, okay, three-phase circuits, they produce three equal voltages, okay, which are out of phase by what 120 degrees. Okay, they are out of phase by 120 degrees. So we'll dive right into this as soon as possible. Okay, right. Now for both the star and delta, these are we represent them. Okay, and then that's why I initially stated that you need to know what, or you need to go through what the topic on what impedance. Okay, in case you've not watched a video on impedance, I'll link them in the description, okay, or up there, so that you get to refresh your mind and then come back to this. Okay, right. So you need to go through that concept and then so that you get to understand this topic. Okay, so we have VC, okay, equal to Vm, okay, sine omega t plus 120. Okay, that's what C. And then for A doesn't have any angle, but for B is at what negative 120. Okay, so whenever you come to the what, or whenever we talk about the line and what planes, the VC, okay, is what whenever it's being represented in what planes and lines, okay, or in what complex number form, that's polar form, we have what the VC, okay, with what, so the magnitude and what the angle, okay, magnitude, angle, magnitude, angle, magnitude, and angle. Okay, for VC is what positive 120, VA as over here had no angle, okay, so 0, and then we have the VB at what negative 120. Okay, now let's move on to the most important portions. Okay, right, the most important, okay, that's what the main formulas. Okay, right. So for star connection, okay, since it's what three-phase, we have what the line voltage, okay, being equal to the root of 3 multiplying what by what the phase voltage, and then for star connection, the line current is equal to what the phase current, and then we already know this formula from what impedance. Okay, V is equal to what IZ. Okay, so the P's are only for what expressing the phases. Okay, right. So and then for what for delta connection, you could notice that there is a big difference. Okay, delta is a bit I could say that the reciprocal of what the star connection. Okay, because you have the line voltage being equal to the phase voltage, but the line current is equal to what the root of 3 times the. Okay, so the line current is equal to the root of what the phase current, and then we have what Vp, okay, equals IpZp. Okay, so these are the main formulas you need to know, and then these are the concepts. Okay, concepts and then formula. Okay, concepts, formulas. Okay, now let's dive right into solving that some questions and then we call it a day. Okay, right. So we have what three identical impedances, okay, connected in what delta across a three-phase. Okay, and then we have what 415 volts voltage supply, and then we have what the line current about 10 amperes. Note that there's what delta. Okay, this is a delta connection. Okay, right, very important, okay, for delta connections, okay. Right, so let's see how we go by this, okay. Delta connection, okay, keep that in mind. That's a delta connection. So with delta connection we use these formulas, okay. Right, so let's dive right into that. And then for star we use this, okay. Right, so let's dive right into the main solution. So let's write out our parameters, okay. So we've been given a certain voltage, okay, of 415 volts, and then we know that it's delta connection, okay, of 3-phase, and then we have so this is a phase, okay, delta phase. So this is VP, and then we have line current, okay, line current of 10 amps, okay. So now we have to find the current in each impedance, okay. So now this is how you find your current, okay. So we know that VP, okay, we know our VP is equal to 415, and then we are line current is equal to 10 amps. So this is how we find out current in each impedance, okay. So we have IL is equal to the root of 3 multiplied by IP, okay. Right, so first we need to find IP because we already know IL, okay. So we know that now IP is equal to IL divided by root of 3, okay. So now IL is equal to 10 divided by root of 3, and this will give us 5.78 amps, okay. Right, so these are the current in impedance. Now let's look at the value of each impedance, okay. Value of each impedance, this A. Now let's move on to B, okay. Value of each impedance, okay. So we know that VP is equal to IP, and then we have ZP, okay. Right, so we are looking at the value of each impedance. So we are looking at ZP, okay. So ZP is equal to VP on IP, okay. Right, so we know our VP to be 415, okay, and then you divide that by your IP, okay, which is 5.78. So when you compute this with your calculator, you end up with 71, okay, 71.80 ohms, okay. Right, so this is quite simple, okay. One thing you need to know is that whenever you are given a question, okay, the parameters which are missing will be used to solve for subsequent questions, okay. So just like here we were given VP and IL, and then IL was used to find IP, okay, and then again IP was used to find ZP because we were already given VP, okay. Let's dive right into the second question, okay. So we have a 3-phase 450 volts system supplies a balanced delta, again a delta connected load of 12 kilowatts at 0.8 power factor lagging, okay. Keep this in mind, lagging, okay. So now we are calculating the phase current, line current, and then effective impedance per phase, okay. Phase current, line current, effective impedance. This is quite simple, so let's dive right into solving that. So let's write out our parameters, okay. Now we have VP, okay. VP, the phase voltage, okay. This is a 3-phase delta, so phase voltage of 450 volts, okay. And then we have phase power or power phase, okay, to be equal to 12 kilowatts, and then we have power factor, okay, to be equal to 0.8. Note that our power factor is also equal to cos theta, okay, lagging, okay. So this power factor is lagging, so keep that in mind, lagging, okay. Lagging could be negative, keep that in mind. Now let's proceed. We are to find what our phase current. Okay, so to find your phase current, you already know that phase power, okay, could be equal to what? Vp, okay, and then what? Ip cos theta. Okay, so this is from what? Power what calculation. Okay, in case you go back to our what video on power calculation, you get to find out. Okay, so we are finding what? Phase current. So this is what we are finding. Okay, so let's make that a subject. Okay, so our phase current will be equal to what? Our power phase divided by what? Vp, okay, cos theta, and then we know that cos theta is equal to what? 0.8. okay, so let's proceed from there. So we have what? The phase power is what? 12 kilowatts. So kilo is what? 10 exponent 3. Okay, so we have 12 times 10 exponent 3. Okay, divided by what? Our Vp, which is what? 450. Okay, 450, and then times what? Our power factor, which is what? 0.8. okay, so when you compute this, you end up with what? 11 amps, or what? 11.8 amps. Okay, now let's proceed to what? The line current. Okay, so this is A, now this is B. So line current. Okay, line current is quite simple. Okay, because we are dealing with what? Delta. Okay, for delta, so just like here we use the line current, okay, from here, right? So that's the same thing we'll be using. Okay, so we have what? Our line current, okay, to be equal to what? Root of what? 3, and then what? Our phase current. Okay, now we have what? Root of 3 multiplied by what? Our phase current. Okay, which is now what? 11.1. so now our line current is equal to what? When you multiply this, you end up with what? 19.2 amps. Okay, now let's move on to what? The effective impedance per phase. Note this, per phase. Okay, per phase, very important. Okay, so we have what? Our C to be equal to what? Impedance. So we know that impedance, okay, is equal to what? Vp, okay, divided by what? Ip. Keep this in mind, per phase. Okay, so per phase we have what? 450, and then an angle of what? 0. Okay, and then divided by what? That's 0 degrees, and then we divide that by what? Our phase what? Current. Okay, so we know phase current what? 11.1 amps. Okay, so we have what? 11.1. Note that this what? The power factor is what? Lagging. Okay, keep that in mind. Our power factor is what? Lagging. Okay, so we have what? Minus what? Cos of what? 0.8. okay, very important. Okay, right, so we have let's proceed from there. So we have when you compute this, you end up with what? When you compute 450 angle of what? 0 degrees, and then 11.1 angle of minus cos 0.8, you end up with what? 40.5, and then an angle of what? 6.9 degrees. Okay, right, so this is because we have what? A lagging what? Power factor. Okay, so this brings us to the end of this tutorial video. You could notice that this was very simple and straightforward. Right, so kindly, in case you enjoyed this video, kindly subscribe to the channel, hit on the bell icon so that you don't miss out on any uploaded video. Like the video and then share. And in case you have any question, just leave them in the comment section and I will reply to them as soon as possible. Have a lovely day. Bye bye.